All right, folks, it's Bass Action back in action here. On this video, we're going to work through from start to finish a complete rotation example. If you are one of my students, you should already have copied this down from Canvas. If you're not one of my students, or if you forgot because you're one of my students, pause the video and write all of this down. It's going to make it a lot easier to follow along than to try to write and listen throughout this whole process. All right, let's start up here at the very top. We're given a conic. The first thing that we would do is we would ask ourselves, what type of conic is this? But before we can even answer that question, we need to ask ourselves if it's been rotated. We can tell that this conic has been rotated because it has this XY term. As soon as we see that, we're going to go through the discriminant process to find the type of conic. Although we could do the discriminant process anytime, it is important to remember that if it's not been rotated, we have easier methods for determining the type of conic. But if you forget, you could always go through the discriminant process no matter what. So it has been rotated with this XY term, so we're going to jump into our first question and determine the type of conic. To determine the type of conic, we're going to do that discriminant, that b squared minus 4ac, where a is the coefficient on the x squared, b is the coefficient on the xy, and c is the coefficient on the y squared. So our b squared minus 4ac gives us our 3 minus 4 times 1 times 2. I've pre-identified the a, b, and c. When we simplify that, we get a 3 minus 8, and our formula that we went through on the previous video, told us that if this value is less than 0, then the conic is an ellipse. All right, so that's our first conclusion. That means that when we're all done, we should have an equation that looks like an ellipse, and if we don't, we know we made a mistake. The next thing that we're going to do is we're going to determine what is our angle of rotation. All right, we want to figure out how much the axes have been rotated. So we're going to follow this formula. Our cotangent 2 theta, and it's a minus c over b. So up here where I wrote my a, b, and c, I always like to link the a and the c because that's a reminder that that's what I'm going to subtract in this next formula. So my a minus c over my radical 3 gives me this expression. What we're going to do is we're going to ignore this 2 theta for right now and just ask ourselves, where does cotangent equal a negative 1 over radical 3? That answer is 120. Then we can take the 2 theta and plug it in here. This step right here is what students often forget. They get that initial 120 and they use that as the rotation instead of doing this one extra step of the 120 equals the 2 theta. So that means that our actual angle of rotation is this 60 degrees. Now we're going to use that 60 degrees in 2 different ways. The first thing that we want to understand is that 60 degrees says that the normal XY axes have been rotated. So if we follow it and we look down here, what I want you to notice is that the X and the Y axis on this grid down here have now been rotated. I've moved them each, keeping the origin the same. I've simply rotated them. So now we're going to use the highlighted axes when we finish our rotation to actually sketch our graph. We also are going to use this 60 degrees to find the new X and Y terms. This is going to allow us to eliminate that XY. So we've got these 2 formulas here, and I introduced them on the previous video, and on the next video, I'm going to go through and develop where they come from. It is very helpful to watch where they come from and understand that because it will help you remember them, and you are expected to remember them. So using that 60 degrees that we found, we're simply going to plug that same 60 in for all of these theta values. You can see I did that here in red. So I have my x prime, my cosine 60, minus my y prime and my sine 60. Then I'll have my x prime sine 60 plus y prime cosine 60. I've already identified and simplified each of those values that were straight from my unit circle, and then I wrote them over here as a single expression. That's going to make it easier for us to work with in the next step. So they both had denominators of 2, so I put the whole thing over 2. Same thing here, whole thing over 2. I've used these primes because those are going to help us keep track of whether it was an original x or a replaced x. Now, our next step that we're going to do is we're going to take these new x and y terms and we're going to substitute them in for all of the x's and y's in this original equation. Okay, so everywhere you see an x or a y, we need to substitute these new expressions. It's going to get messy, but I'm going to show you a good way to organize your work so that you can keep track of it. So now I'm going to slide this up a little bit, and I want you to follow along and just make sure that you can see this right here is my x term, and I've put parentheses around it to square it. This is my new x term, this is my new y term, and I'm following this. This is my y term, I squared it. And then I also have to be really careful to remember to include any of these other coefficients around here. Those often get forgotten, so don't forget, there's my radical 3, there's my 2, and there's my negative 10. Any of those coefficients or constants are very, very important. The other thing you'll notice that I did in organizing my work is, since these are all going to be fractions for us, I went ahead and I wrote each of my coefficients here also as fractions over 1. It's just going to help us keep everything properly aligned when we're trying to simplify. The other thing that I've written here is kind of thinking ahead that when I expand this expression, or I FOIL these, or I expand this one, I'm going to end up with a new denominator on all of these of 4. So what I want to do eventually is clear out that denominator of 4. So here in purple, I've written this 4 because we're going to use that over and over and over again. So I want you to recognize that this 4 right here is going to be this same 4 all the way down, and it's going to allow me to clear these fractions in the next step. Now we're going to start our expansion. What I want you to notice is that when I expand these, we're going to go through this stacking process. This isn't mandatory, but it is strongly encouraged because it definitely makes the whole thing easier. I'm also going to do some of the algebra in my head. If you want to write a little more down, you can. And then the last thing is that even though each of these expressions have these primes, when I get down to this step, and I'm going to have a value that's primed and squared, I am not going to write these primes throughout this process, just because it's a little harder to keep track of. So I understand that they're supposed to be there, and I can always put them in the end, and it might help you as well to drop them in that middle step. All right, so here we go. What I want you to first see is that this expression right here, okay, this whole one, I need to square it, and it's going to become this one. Remember, when we square something, we have to multiply it by itself. So we're going to actually have to FOIL that entire numerator. So if I rewrote this numerator again, I would be able to see I would get an x squared. I would have this product twice, and I would square this, and the radical 3 squared becomes 3, and of course my 4. And again, pull down that 4. On the next step, I'm going to FOIL all of these. So as I FOIL this, now this one's a little easier because it's already there. So when I FOIL that, I am going to get this whole expression. So just going through my foiling process, all right, I end up with my x squared, radical 3x squared, then the 3 and the radical 3 times the radical 3 is going to give us a 3, but so the radical cancels, and this is a 1, so I have 1 is my coefficient, and then I have a minus 3 is my coefficient. That's where this negative 2 is coming from. And then when I FOIL these two, I have a negative radical 3 squared, still have the 4, and I still have this radical 3 over 1 here still has to come down here. The next one I'm going to FOIL again, and I'm going to FOIL in my head again. So just like I did on that x term, I'm going to FOIL this in my head. And when I FOIL this, remember I am multiplying that numerator by itself. When I FOIL that, I'm going to get a radical 3 times itself is 3. That's where my 3x squared comes from. This product twice is where that's coming. And then the y squared. Still over 4. And I still need this 2 to be right here. The last one is this constant, and these often get forgotten. So there's my minus 10 right there. And then I'm going to say it one more time. Remember, this 4 to clear the fractions has to come all the way down. Now the next thing we're going to do is we're going to expand everything out. So these 4's are going to cancel, so the numerator is all I have left. These 4's are going to cancel, but I'm going to distribute my radical 3. So I'm going to get my 3, my minus 2 radical 3, and then a 3 again. These 4's will cancel. I can distribute the 2, and I get this expression. And then, of course, a negative 40. Now, if we did the entire process correctly, and we have stacked each of these, our xy terms should all nicely line up, and they should all cancel each other. They should add to a nice 0. If they do not cancel each other out, then you have made a mistake somewhere along the way. Collect all your like terms, and we get to this step right here. We can tell that this is going to be an ellipse, same signs, different coefficients. If I divide everything by 40, because this will become my 1 on the other side, I get my final rotated expression without the xy term as this very, very simple conic. Which means I can just quickly read from that on my rotated axes, the distance from center will be 2, the horizontal distance, and the distance on the vertical axes that have been rotated will be a square root of 20, and you can just approximate that as 4.5, just call it good enough. So you can see that's exactly what I did over here. I went 2 in each direction on the x, and I went about 4.5 each in direction on the y, and I have my rotated conic. And if you type this conic, the original one, into Desmos, it'll look just like that.